We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
For nearly 60 years, we've been visiting the heavens, sending spacecraft far beyond our own world. We've seen the beauty of our own planet and captured breathtaking images of worlds millions of kilometers away. Work aboard the International Space Station is preparing us to return to the moon, and then to take mankind's next giant leap to Mars. We stand at the dawn of a new age in space exploration. The countdown is now on for a manned mission into deep space, to the space station and beyond. For years, scientists and astronauts have been living and working above our planet in the International Space Station. Here, they enjoy a heaven's eye view of Earth. Since 1961, over 400 people have ventured into space. The rest of us rely on their pictures and first-hand accounts to feel the thrill of space travel.
Tokyo.
Tokyo Bay?
Yes.
Yeah. You got it in there?
That's cool. Are you cool?
It's an unforgettable memory for the few who have made the voyage.
Mount Fuji there.
Can you see the moon at the same picture?
Yes.
And every time you look at it, it's different. And even if you're over the same place on the Earth, you know, multiple times doing a mission, it looks different every time. So, you know, the visual splendor is absolutely constant.
It's a great honor to be among that group that's been able to fly in space and see the Earth from that ultimate high ground.
America's space agency, NASA, hopes the high-definition TV images now being shot on board the International Space Station will allow people to feel as though they are actually there.
Space is real, and we live in space, so capturing that through high definition brings us closer to being there. And that's an important element of space exploration.
The human eye is a pretty amazing device, and it can see lots of fine detail and fine color structure. HD gets us closer to what you can see with your eye.
One of NASA's main missions has always been to share the fruits of space exploration with the public. In the early days of spaceflight, this meant relying on older video technology, which often made for some fuzzy viewing. But now, with high-definition TV, the days of grainy images transmitted from space are ancient history.
The first HDTV camera that was flown in space was flown on STS-95. It was the John Glenn mission. And I do remember it very vividly, and everybody in the room, it was almost electric for them watching this video, because all of us had been involved with NASA video for literally decades, and it was nothing that we had ever seen before. It was just incredible.
But it's not just about pretty pictures for the public. NASA believes the sharper images will also help researchers on the ground learn more about our own planet.
If you look at like a sunrise or a sunset, and you can see how thin the atmosphere really is, you know, that little thin blue atmosphere is what keeps us alive here on the Earth. I think you get an appreciation of how fragile our planet really is.
I think for Earth sciences, it does a couple of things. It allows us to get a moving image, where they do an orbit of the Earth, to get things in better perspective than you might get with still images.
HDTV has an important role in monitoring scientific studies in space as well.
It's accurate enough that we can actually use it for measurement purposes, which you can't do with analog video. There's too many inaccuracies in analog video.
HDTV has left the Earth and has traveled to the space station and beyond.
We're now in the HD era here on Earth. Television, movies, and all that. We are really also moving into the HD arena in space for the public. Not only at Mars, not only at Space Station, but also at the Moon.
For years, unmanned probes have been our eyes and ears in space, loaded with imaging and sensing devices of every sort. They've sent back spectacular images of deep space. From the rings of Saturn to the moons of Jupiter. But the one planet that has always held a special attraction for us is Mars. And now, it's not as far away as it once appeared. Those of us who live on Earth have always been intrigued by Mars. And the more we learn about the Red Planet, the greater our fascination.
Well, Mars has been the beguiling planet. Mars has tricked us every time. We saw it at first, and we're disappointed. It looked lunar. And then we saw it a decade later, in the early 70s with Mariner 9, and we saw a world of fantastic possibilities. Big canyons, mountains, ice caps, wow. And then we went, with our eyes wired shut, with Viking, looking for those perhaps obvious signs of life. And now, in retrospect, realizing that the planet was more tricky, more beguiling than that first foray. Nonetheless, Viking opened our eyes to the real Mars. Cold, perilous, and yet fantastic, dynamic, nothing like the Moon. And rightfully so, the Moon being a planet in its own right. And then the next wave of exploration, beginning in the middle 90s with the Pathfinder, with its Sojourner rover, and then the Mars Global Surveyor. Ironically, the Global Surveyor is still there, still working. I wish my car worked so long.
Though only about half the size of Earth, Mars is a world of enormous valleys, swirling dust storms, and vast ranges covered in a blanket of reddish dust. And it's only about 80 million kilometers away.
We should go to Mars for a couple different reasons. One is, for planets, it's close. So it's accessible, and we can actually, robotically, we can send a spacecraft every 26 months. So we can build up an infrastructure there. It's another place where life might have started. So scientifically, there's lots of things that we can learn about Mars that'll help inform us about our planet and what life is. And then the final reason for going to Mars is we need to have humans on another place if we're to continue beyond whatever the lifetime of this planet is, which is, on the order of 500 million years.
Going to Mars will be like building a cathedral. You have to stick to it. Any perturbation, any lapse in support, you'll lose the ability to do it. And just remember what going to Mars will be like. It'll be like launching a mass equivalent to the space station to carry 4, 5, 6 women and men to Mars and bring them back. And we still haven't finished the space station. Mars is the nearest hard place to get to where we can sensibly ask questions that relate to our own existence. Our history of exploration changed with Mars as we've looked at it through different lenses. Today, we are so privileged to have 5 working space systems robotically exploring Mars, the people here, the machines there.
Man's quest to reach Mars began in the early 1960s. Today, that pursuit continues with the Mars rover program.
And liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
On June the 10th, 2003, the rover, Spirit, took off from Mars.
Vehicles responding. Vehicles recovering very nicely from the liftoff transients.
Her sister lander, Opportunity, followed 7 days later. Their mission? To explore the surface of the Red Planet. On January the 3rd, 2004, Spirit became the first robot to land on Mars in 7 years. It arrived at a speed of 19,000 kilometers per hour. The craft slowed to about 3,000 kilometers per hour once it hit the Martian atmosphere. About 2 minutes before landing, the heat shield was ejected, Just seconds before touchdown, airbags were inflated, retro rockets fired, and Spirit was released, surrounded by its protective cushioning. The landing was the equivalent of a galactic hole-in-one. Despite bouncing 27 times to a height of over 9 meters, Spirit landed just a few kilometers from the center of its target area. The vehicle bounded for about 275 meters before stopping. Emerging from her protective cocoon, Spirit slowly spread her wings and went to work. It was hoped the rovers would study the Martian landscape for 90 days. But 3 years later, they're still going strong.
What they've done is not only fulfill their primary mission of helping us understand the ancient water history of Mars, but really help fill in a lot more. We've been able to determine that, yes, indeed, there was a lot of water on the surface of Mars at some point in the ancient past. We can actually see traces of the water history in the rocks themselves.
Mars literally weeps fluids, likely water. It has ice sheets. Odyssey showed us it has buried ice sheets of great expanse. Mars is a water planet. It's appropriate to ask the question, was Mars ever alive? Is it alive today?
We've also been able to determine that indeed Mars was capable of having a life-sustaining environment in its ancient past. And that has been something, again, that was a question that we had sort of said, we think we know the answer, but we don't have hard evidence. These rovers have given us the hard evidence to say the environment really was one that was capable of supporting life. We also want to understand, are there resources there? Are there things there, for example, that an eventual human mission might be able to use in terms of long-term survivability? And also the big question out there is we want to understand, is there life on Mars? Was there ever life on Mars? If there was, did it evolve? And try to understand what the environment was like and its capability for supporting life. If it wasn't there before, is it at least there in a fashion that would allow us to have supportable human presence?
Spirit and Opportunity are the latest probes in NASA's continuing exploration of Mars. Loaded with research tools, the robots are sending a steady stream of valuable data back to Earth.
The rovers are designed to be able to operate on the surface of Mars completely autonomously with just a regular series of sort of daily command uplinks from Earth. Basically, the scientists are able to use the cameras on the rovers as their virtual eyes, see the rover's viewpoint of the environment, pick out what targets they would like for scientific investigation, send those commands up, and then once a day we'll get the results back from the rovers having completed the commands that we gave them.
The rovers were designed to travel about 40 meters each day. They have far exceeded those limits. By December 2006, Spirit had covered more than 7 kilometers of rugged Martian terrain, following the directions of scientists on Earth.
On some days, we may just tell them to drive. We tell the rover, we know that you're here, we want you to be over there, you drive there, get there on your own, and then when you're finished, just let us know. The rover has enough intelligence on board to be able to complete that command and navigate around hazards and avoid obstacles all by itself. On other days, when the scientists may command the rovers to do remote sensing, there's a set of cameras on board the rover that are on top of the mast that allow us to look around the terrain sort of from a human eye vantage point. The cameras are literally almost at human eye height. So these images that we get of the surface of Mars as the rover looks around are the same as if you or I were standing on the surface of the planet and looking around. It's from that vantage point. And that helps us understand the context as well as the detailed resolution of the surface of Mars. These cameras are literally capable of 20/20 vision.
It's almost as good as being there. Images from overhead, images from spectrometers and interferometers are very interesting and they teach us a lot. But for the average person, a human's eye view of the planet is really the way we would see it if we were there, and makes the rovers extremely exciting to the public.
Although still gathering valuable data, time has taken its toll on the robots.
On Spirit, one of her front wheels, the actuator, the drive motor, has locked up. And so we basically have to drive her by sort of moving backwards and dragging that one wheel. On Opportunity, a couple of the instruments are beginning to have some of their emission sources decay over time, and so we treat the way we conduct the actual science observations a little bit differently. So again, a little bit of personality differences between the two in terms of what we do with them. Now basically sent them on their way, they're on their own, they're going to do what they're going to do. Sort of like when you send your kids off to college. You've done the best you can up until that point to train and educate them. You've now cast them out on the world, and they're on their own based on what you've taught them up until that point. They've been great students so far. Now we're just waiting to rent out their rooms.
Just months after the rovers began their close-up study of the Martian surface, another probe was sent to study Mars. On August the 12th, 2005, an Atlas V rocket was launched on a new mission to the Red Planet. But the destination wasn't the Martian surface, it was the Martian skies. And after 13 months, the Mars Reconnaissance Orbiter, or MRO, began scouting landing sites for a future manned mission to Mars.
The Mars Reconnaissance Orbiter is a science orbiter. It's one of the most sophisticated orbiters we ever had around Mars. It's to study the geology, it's to study traces of water. And this is it's a key element of our path to the future, for us to understand Mars and then for us to understand where we want to send our future missions.
It took 7 months to get the MRO to Mars and 6 months to slow it down, using a technique called aerobraking.
Using the atmosphere during those 7 months period or so to slow down the spacecraft so we could put the spacecraft in the correct orbit of about 200 by 300 kilometers elliptical orbit around Mars. Aerobrake is a one-time event to save fuel. We'll save a tremendous amount of fuel that we would have taken if we did not do the aerobraking with the atmosphere.
Spectacular. This is our HD imaging lens on Mars. Every image its high-resolution camera, known as HiRISE, takes is another landing site experience with a resolution, the scale that the Mars exploration rovers see at the scale of 20, 30 yards away from orbit. We can see thousands, if not 10,000s of places, and then we can put them in context. So MRO is poised today to start a whole new campaign on Mars, opening our eyes to why we need to go. It is going to be the site finder.
Getting a very high resolution allows you to look at the planet without actually having to stand there and look at it. And at this high of a resolution, for the first time, we can now see rocks of the same size that are dangerous to landing spacecraft. So now we can actually image the spot where we think we're going to go and look and see whether or not there are rocks that are big enough to hurt the landing spacecraft.
The imaging system paints 2 pictures, a wide shot to provide context, which is then layered onto the very high-resolution images of the planet's surface. The MRO camera is so powerful, it can see and track the rovers below.
The Mars Reconnaissance Orbiter that just arrived at Mars provides us an entirely new window on the planet. One of the first things that we did there that shows the power of robotic interaction of missions is we looked for the Spirit and the Opportunity rovers. Now that may sound like just something interesting to do, but in fact, the ability to image a rover as small as 6 feet across from space provides us not only the ability to find it and understand where it is, but it helps us build traverse maps. In other words, plan the routes that we would like the rover to take, such as Opportunity exploring the region around Victoria Crater and getting into Victoria Crater.
So we're not just going out there and saying, all right, well, nice pictures. We're trying to understand what happened on our sister planet so we can try to apply and understand if any of those events could occur here on Earth.
But while machines help plan a manned mission to Mars, will humans be up to the demands of the trip? That question is being answered on the International Space Station, or ISS. The station plays a critical role in our ambitious designs for deep space. It's a laboratory in the sky where we're learning about the science of space and the effects of long-term space travel on humans. In December of 1998, construction of the ISS began when the Space Shuttle Endeavour carried the Unity module into space. In a delicate and unprecedented maneuver, Unity was joined to a Russian module already in orbit.
Oh, this is nice. Keep her coming, and out the window view is awesome. There's about 14, 15. Drive your mirrors off. Good job.
We've got Unity firmly attached to Ross. Great start on building the International Space Station.
And so began the most ambitious and audacious scientific project in world history. The ISS is a cooperative venture among 16 nations. It's a work in progress. When finished in 2010, it will consist of 10 main pressurized modules connected to a large truss system. A number of smaller modules and visiting spacecraft will also dock at the ISS. The surface area of the solar panels alone will cover 4,000 square meters. When it's completed, the station will weigh more than 350,000 kilos and will be 50% larger than a football pitch.
Next year will be an extremely busy period on board Space Station. We'll increase the weight. We'll also add Node 2, and we'll add the international partner modules next year.
I think the greatest thing ISS can do is really be that permanent beachhead in space that teaches us how to go beyond. It's the Canary Islands to the Columbus trips and the Magellan trips. A 2-week shuttle mission, great as it is, and they have been, doing so many things, even mapping the whole Earth with radar as they have, still not the same as living in space 6 months or a year. And so a space station is a right step.
It will take more than 1,900 man-hours to complete the job. Because of its size, it has to be assembled in space, piece by piece. It's a painstaking process. To finish the job will take more than 100 space flights and 140 spacewalks. And outer space is not your average construction site. In outer space, there's no atmosphere to temper the radiant energy of the sun. That creates a drastic variance in temperature between sunlit and shaded areas.
In the shadow of the space station, you might be working with tools that are minus 100 or 120 degrees, below 0 Fahrenheit. On the hot side, in the sun, you might come into contact with things that are 250 degrees above Fahrenheit. And above that, you'd start to melt the spacesuit glove, and that's something we'd like to avoid as well.
The temperature difference between these two astronauts working side by side could be nearly 200 degrees Celsius. Fortunately, their spacesuits protect them from these extremes. But while the work is hard, it has its perks too.
The space station was a great place to live. It actually was fairly roomy. It was about the size of 4 school buses rammed together, but with holes cut between them, so you could float almost 200 feet from one end to the other. Floating from one place to the other is so effortless and zero gravity. So it's really fun, and I never got tired of, if I had a spare second, of just doing a flip.
The International Space Station is in orbit approximately 360 kilometers above the Earth, traveling at a speed of about 28,000 kilometers an hour. At that speed, it circles the globe once every 92 minutes. When complete, it will be visible to 95% of the Earth's population. But even in its unfinished state, the ISS plays a critical role in preparing us for deep space travel.
Things we're doing on Space Station today will be needed when we go to the moon. They'll be needed when we go to Mars. If we have a part that breaks, we can fairly easily fly it to Space Station. To fly that same part to the moon is not nearly as easy. To Mars, it's almost impossible. So you can think of it kind of like a stepping stone. We're kind of getting further and further away from home. We need to learn to operate with those ties to home broken. And Space Station gives us a first chance to go do that and demonstrate that we can do that before we have to go do it on the moon, and then before it becomes mandatory for Mars.
The lab module is called Destiny, and this is where we do the bulk of our work here on the U.S. segment.
The station is an invaluable resource for studies that could never be done on Earth. On a recent flight, astronaut Mike Lopez Alegria demonstrated a few.
Here are a couple of experiments. One in particular is pretty interesting. This European delivered MELFI, which stands for minus 80 degree laboratory freezer. It's in fact closer to minus 100 degrees right now, and I thought I might show you where we like to keep our ice cream if we had any on board. It's about a minus 100 degrees centigrade. So it's quite cold. One of the things that we're very interested in, of course, is what happens to the human body as we are subjected to long periods of microgravity. And we can measure what we intake by basically notating everything that we eat or drink in a certain period. And then our blood samples correlate how our body is processing those. And of course, the blood samples we can't analyze on board, so we freeze them for later analysis on the ground. This experiment is called Spheres. It's a satellite system. We have a couple of them, actually. It uses CO2 gas to maneuver itself, and we can actually get these two satellites to fly in formation with each other and actually dock to each other. So that's a pretty fun experiment.
The ISS has already provided scientists with a wealth of tantalizing data. The laboratory of space has opened up lines of scientific inquiry that were unimaginable just a few years ago, accelerating the development of treatments and cures for a wide range of acute and chronic diseases.
The results we're getting in tissue culture using controlled gravity systems is already putting key pieces of the puzzle of tissue engineering together, a day when we will be building organs to order from a person's own tissue.
For some reason in space, liver cells will actually produce a liver if they're grown in space. They won't just form a glob of cells. They'll actually form into a structure like a liver. And that's not important. We don't want to grow livers in space. But what we're trying to understand is what mechanism occurs in zero gravity. Is it radiation? Is it the zero gravity? Is it something in the atmosphere? What causes those cells to behave in a different manner?
The complex demands of building, working, and living on the space station have also spawned remarkable advances in technology, especially robotics. Small floating, voice-directed personal assistants, virtually controlled robonauts, and the massive remote-controlled robotic arm are all examples of tools and technology created by human necessity and purpose.
I think probably space station is really a testing ground or a proving ground to test out engineering concepts, to essentially learn. So as like maybe early explorers got in sailing ships and sailed and they learned and then carried those experiences to the next generation, I think space station can do the same kind of thing for us. It can be a training ground, a proving ground for us to learn new concepts.
But while we can invent a new machine to help us reach distant planets, we can't invent a new human body. So, perhaps the most important research taking place on the space station concerns the ability of humans to physiologically and psychologically withstand the rigors of extended space travel.
The adaptation of humans and complex life forms to space is one of the first hurdles we have to overcome, and an important reason why we want to go to the moon, to understand how to get to places as far away as Mars.
The trip to Mars is about a 6-month trip, which is about the duration of my stay on the International Space Station. So the space station becomes our analog for a long-duration transit to Mars.
One area of great concern is the loss of bone mass that occurs with prolonged space travel. In the weightlessness of space, astronauts' bones don't need to support their body weight. This causes muscles to atrophy and bones to deteriorate, leading to a condition called disuse osteoporosis. In fact, astronauts lose up to 1.5% of bone density for every month spent in space. To minimize that loss, they exercise on a specially outfitted treadmill and other equipment for up to 2 hours a day. But bone loss isn't the only concern.
Another one is radiation. The radiation environment is fairly high in space, and we need to look at how we can protect the human from the radiation environment and understand it a little bit better. That also may lead to some basic research in the cancer area as cells mutate or change. And then the third area is just being kind of removed from your family, removed from normal day-to-day things on the Earth.
Not being able to see Earth. Earth's going to be just this little speck out there in the distance, as opposed to, when we fly around it in low Earth orbit. I mean, it's big, it's close, and we could get back home in hours if we needed to. Mars, you're gone for a long time. So there's some psychological issues that we're going to need to deal with also.
The terrain below, how would I say it? It is an experience that makes you really appreciate what we have down there, that it's fragile, that we need to protect it, and you feel very detached from it, and sort of you miss it. It's your home, it's where all your loved ones are, where all of your experiences have happened, and you really get a sense of being separated from it in a way.
The human beings we send into space are explorers, astronauts, and yet we use them also in some ways as patients. They are patients. And as patients, we watch how they do with non-invasive monitoring and things like that. It's important. They are at the edge of the envelope of that frontier in space, so we need to know how well they do.
I like it so much.
One of the most immediate issues deep space travelers will face is nutrition. The success or failure of lengthy future missions could very well depend on the space station menu.
Our food comes in a variety of different forms. Some of it is dehydrated, and some of it is thermal stabilized. Some of it comes in its natural form. This is soup before it's dehydrated. It doesn't look particularly appetizing. And this is soup. It's noodle soup with meat after it's been hydrated. It looks a little bit better. You can choose to eat this soup with a spoon if you'd like, but it's more practical just to use this sort of built-in straw device.
Well, living in space today is done on the International Space Station. Part of the experiment of living in space, the experiment we need to do to be able to go beyond living on the moon, onto Mars, involves such, in some cases, mundane things as nutrition.
Nutrition has always played a vital role in space exploration. Since the early days of powdered juice and freeze-dried chicken salad, food systems have evolved along with the space program.
So we actually have our salt, pepper, soy sauce, and actually some wasabi in a different sort of a form. This is actually salt, and in order to apply it, you just remove the lid and squirt some. You can see some of it is caked on the outside, but you just sort of squirt some.
In preparation for future missions that will take us beyond Earth's orbit, researchers continue to use ISS to study the effects of long-term spaceflight on the human body.
We have nutritionists, nutritional experts, physiologists, all working together to see how do we make the living in space experience the most healthful, the most long-term sustainable. Because the trips to places like Mars eventually will require multi-space station scale rotations to undertake them. I mean, as far as we can imagine today, a trip to Mars would be equivalent to 2 full 6-month rotations on a space station, if not more.
By monitoring astronauts on ISS, scientists now know that extended periods of weightlessness can severely impact the human body. So watching what you eat is even more important in space than here on Earth.
This is orange pineapple drink, and of course, you got to be careful. I would be remiss if I didn't do the obligatory orange bubble trick. Fluids in space end up taking the form of spheres to reduce the, or due to surface tension. And you can sort of play with it as much as you want. You can blow on it to get it to do certain things. But the best thing to do with it is eat it.
We monitor not only the intake, of course, of calories and foodstuffs for energy, which is needed to undertake the activities, but we also watch indicators on the crew as they go and return. Bone loss, muscle decay. So nutrition is part of the equation of living and working in space.
Preparing for human missions into deep space will require a multitude of technological advances, not only the right diet. This is one of the many valuable lessons we're learning on the space station.
That kind of idea, using the space station as an element in the trip to Mars, could be invaluable. But again, we do not, at least from my understanding, have full depth of knowledge on what it will take nutritionally, in terms of diet, for the long Mars trips. We're just learning on space station what works best. And that's why space station is so important.
While the space station is helping prepare us for long-term space travel, unmanned missions will also get us ready to go to Mars.
We have a wonderfully robust robotic program of sending a spacecraft at every opportunity to Mars. And in fact, one of the things that we need to learn about Mars before we send humans is what is the biological potential of Mars. Because you don't want to send humans to Mars if there's Martian life on the surface because of the potential contamination of contaminating the red planet. But also, you don't want to send humans to a place where they might become infected with Martian microbes or carry with them microbes back to Earth. So you want to know for sure whether or not there's any biology there.
The upcoming Phoenix lander mission may answer these questions.
Phoenix is a lander similar to the Viking spacecrafts that's going to land on the north latitudes of Mars near the North Pole. It complements our scientific observations by looking mostly at the surface soil and to try to see if there are materials in there that we could identify with water, or try to understand the chemical composition of the soil, but in particular trying to see if we also can scrape some ice.
It will tell us a lot about the ice structure and potentially the habitability of that ice in the northern polar region, an area that's of very great interest because of water captured by the ice caps.
Phoenix's robotic arm will dig into the red planet's subsurface to collect ice and soil samples, which will be analyzed on the spot. Phoenix will help scientists determine whether or not Mars can support life. Laser light pulses will scan the Martian atmosphere for ice and dust particles in an effort to learn more about Martian weather. Step by step, we're learning more about this mysterious planet. The ultimate task of carrying astronauts to the moon and beyond will require considerably more muscle than the power needed to send unmanned probes into space.
When we look at sending robotic spacecraft, we are dealing with missions that are on the order of a metric ton or 2 metric tons in terms of payload. For sending astronauts, one of the scenarios ends up being something like 60, 70 metric tons. So that's a lot more stuff.
To carry that stuff, NASA is developing a new class of rockets named Ares that will be ready to use in its upcoming lunar mission. The Ares 5 is the heavy launch vehicle that will carry the lunar lander into orbit. At 109 meters, it's nearly twice the height of a space shuttle with its boosters. The Ares 5 will lift off using a pair of 5-segment solid rocket boosters attached to a single liquid fuel booster, similar to that used to launch the space shuttle. The Ares 5 will have the power to lift more than 100 tons into Earth orbit. After 2 minutes, the spent solid boosters will separate and fall back to Earth, where they'll be recovered and reused on later flights. The shroud will separate, revealing the lunar lander. The liquid booster will drop off, leaving the vacant lander in Earth orbit, where it will await the arrival of its crew. The crew launch vehicle is the smaller Ares 1, which will carry the Orion capsule into space. Although it looks like the old Apollo, the Orion is much larger and will carry up to 6 astronauts on board. The Ares 1 has a 20-ton payload capacity. So in addition to carrying crews into space, it can also be used to shuttle supplies to the ISS or to place loads in orbit to be retrieved later on. The Ares 1 has 2 stages. The first is a single reusable solid rocket booster, like those used on the larger Ares 5. Midway through its flight, the reusable booster will separate, and the Orion's abort engine will jettison. The upper stage engine will then ignite and separate, hurling the Orion into orbit. The Orion has two parts, the crew capsule and a service module to carry supplies. Once in orbit, the unit will maneuver into position to rendezvous with the waiting lunar module. Although it can carry a crew of 6, for lunar missions, Orion will carry 4 astronauts. Orion will be able to handle missions up to 6 months long, the length necessary for future flights to Mars. A series of delicate maneuvers will allow Orion to dock with the lunar module. The Earth departure stage engine will ignite, allowing the docked vehicles to escape Earth's orbit and head to the Moon. The trip will take 3 days. When the craft arrive, the engine will separate, leaving the 2 docked vehicles in orbit around the Moon. All 4 crew members will move to the lunar module, which will separate from the Orion capsule and begin its descent to the lunar surface. The empty Orion will remain in orbit, 100 kilometers above the Moon. Rockets on the lower descent stage of the lander will control the rate of descent. The module will land near the lunar pole, which may be the site of a permanent base. As it approaches the surface, its engines will slow it down until the module gently lands on the surface of the Moon. One by one, crew members will climb down the module ladder. And after a hiatus of more than 30 years, man will again set foot on the lunar landscape and enjoy a privileged view of his home planet. Returning to the Moon is a critical step towards an eventual manned mission to Mars. After landing, the crew will make a half-dozen Moon excursions to conduct experiments, collect samples, and take pictures, all with an eye toward building a permanent base in the future.
Establishing a lunar colony would be useful to help us understand the processes of living on the surface, how we would conduct business on the surface, how humans survive in a higher radiation environment than on Earth, as well as a lower gravity environment than on Earth.
Certainly, the lunar trips will provide valuable lessons for future missions to Mars, but there are immediate benefits as well.
Are there resources on the Moon that could allow us to live off the land? And so we'll be looking at that scenario also. The lunar regolith has oxygen that can be removed and used for life support or potentially to make rocket fuel. So those capabilities will be explored while we're on the surface as well.
When their work is done, the astronauts will re-enter the lunar module. The ascent stage will fire its engines, leaving the lower stage on the Moon, where it may be used to build a platform in the future. The module will then rejoin Orion in orbit, and the 2 craft will again dock. After transferring the samples and equipment, the empty ascent module will be jettisoned, and the Orion will begin its 380,000-kilometer journey back to Earth. When Orion reaches Earth's atmosphere, the service module will be jettisoned. The capsule will be traveling at about 40,000 kilometers an hour. It will be placed in a specific trajectory to slow it to under 500 kilometers an hour. Once safely inside the Earth's atmosphere, 2 chutes will slow the capsule. The heat shield will be ejected, and inflated shock absorbers will deploy. As it approaches the Earth, 3 secondary chutes will open, and the first 2 will be ejected. The capsule will continue its gentle descent, and, unlike the Apollo capsules that landed in the ocean, the Orion will make a soft landing on the Earth. NASA's goal is to return to the Moon by 2020. How long before men and women walk on Mars is unknown. What is known is that they are determined to do so.
The idea of landing people, women and men like us, on Mars is akin to the greatest voyages of discovery ever made by humankind. We have to think of it in perspective. The Renaissance exploration of this planet took us so far, thousands of miles to new lands. Imagine then the scale difference from going as far as we've gone with humans to the moon, to low Earth orbit, the space station, to Mars. It's a factor of thousands. We've never made that leap in exploration ourselves.
There's a lot to go into a Mars mission because the moon is far, Mars is much, much farther. So a 3-day journey to get to the moon, to Mars, you're talking about 6 months. And then once you go, you have to stay for a long period of time. So it's order of magnitude more difficult, and that'll take a while, but I don't doubt that we will get there.
How quickly can we transition from the space station legacy to the moon legacy to getting us to Mars? And that is what the vision of space exploration is all about. Building if you will, the stepping stones. And how quickly can we leap? And until we start trying, we're not going to know.
One of the turning points in the NASA story was the tragedy involving the Space Shuttle Columbia. Astronaut David Brown kept a unique video diary of the training he underwent.